Okay, so here we have a solid disk that is on a ramp at an angle of 20 degrees, starts out 3 meters high. And I didn't write this here, but we're going to have this thing rolling without slipping. So no slipping is going to occur here. And there's two questions that I want us to figure out. One is what will its acceleration be? And two, what is the force of friction that's acting on it? So there's several ways that we can do this, but let me show you a method using torque. So I'm going to draw a free body diagram of the disk that I can use with the torque equation. So that means I need to draw all of the forces that are acting on it at the exact location that they're actually being applied. So certainly there's a force of gravity that's acting on the disk. We draw that coming from the center of mass. There is a friction force acting on the disk, and that's going to be parallel to the ramp, and it's going to be therefore tangent to the disk itself. And finally, there is a normal force that would be perpendicular to the ramp. So that's what the three different forces acting on the disk look like. And so now what I want to do is I want to apply those to the equation angular acceleration equals net torque over rotational inertia. Of course, in order to do this, in order to calculate torques, I need to know where the axis of rotation is. And here's where a unique thing happens in this problem. That probably your first instinct is to use the center of mass as the axis of rotation, because certainly as a wheel turns, it rotates around that axle. But that's actually not 100% true when you look at it from the frame of reference of the Earth. And this is hard to illustrate on a piece of paper, but maybe you can play around with a wheel yourself. That basically the bottom of the wheel touches the ramp or a tabletop or the ground. And as something rolls forward, it really is rotating around the point that's making contact with the ground. Now, that point is constantly changing, but for a brief amount of time, this entire object is rotating around this point that is touching the ground. And so you can use this location, the point where it touches the ground, as your axis of rotation. And that has a benefit here because when you put your axis of rotation at that location, the force of friction is acting at that location. And that's an unknown. We don't know what that's equal to. And because it's acting right at this axis of rotation, when you go to calculate its torque, torque equals Rf sine theta, the R for the force of friction at this axis of rotation would simply be equal to 0. So friction doesn't exert any torque when we put the axis of rotation right here. So that's going to make our equation easier to deal with. So let's see what that ends up looking like. So actually, neither friction nor normal force exert a torque because they have no radius if we're using this as our axis of rotation. So the only force that's exerting a torque is the force of gravity here. And the distance between the axis of rotation and where the force of gravity is being applied is just the radius of the disk. The force itself, of course, is equal to mg. And there is an angle here that's not 90 degrees. So we have to take the sine of that angle. It turns out to be the same as the angle of the ramp. And maybe I can just quickly prove that to you by going over to this drawing. So we're talking about this force right here. That's the force of gravity. And we're comparing it to the normal force right here, which is there in that diagram. So this is small. It's hard to see. But basically, if the 20-degree angle is here, this is 90. That makes this angle a 70-degree angle. And so directly across from that is also a 70-degree angle. And up here, that's going to be the complement of 70, which is a 20-degree angle. And that's the angle that I've labeled right here. So it's the same as the ramp angle. One final thing, which is if you want to be careful about positive and negative signs, the torque that gravity creates with a radius in this direction and a force in that direction is going to be a negative torque. Another way to look at that is gravity is going to have a tendency to make it rotate that way. And when something rotates in that direction, your thumb points in, and that's the negative direction. So if we're concerned about signs and not just magnitudes. It is technically a negative torque. Now, there are no other forces that are creating torques, so we're finished with the top of the equation. Bottom of the equation is the rotational inertia. Now, it's a solid disk. If you look up the rotational inertia of a solid disk, you get 1/2 mr squared. But here's a really important part of this problem. That's the rotational inertia if it's rotating around its center of mass, which is here. And we're using a rotation point on its rim. So we have to use the parallel axis theorem, which says we take the rotational inertia around the center of mass and we add to it mh squared. And h is the distance between the center of mass and where the new axis of rotation is. And that's actually just the radius of the disk. So very, very important when you solve it this way, the rotational inertia down here is around that parallel axis. It's not around the center of mass. The other thing we might want to do, since we're trying to find linear acceleration, is just replace alpha with a over r. They're equal to one another. Alpha is equal to a over r. One of the things that does is it allows us to cancel out the radius. You'll notice we weren't given the radius of the disk. So let's say this radius cancels out the squares, and then this radius cancels out the remaining radii. We can also cancel out the mass, so this mass cancels out this one and this one. One thing to be careful about here, you'll notice I've canceled every single term here, but the way mathematics works is canceling is really dividing something by itself. So this is now not 0, this is now simply 1. That's the number 1 there. So we have 1 here, and we have a half here. So inside the parentheses, we actually have 3.5. In fact, let's neaten this up a little bit. We have a equals negative. G, of course, is 9.8 times the sine of 20. By the way, that all by itself would be the acceleration of an object that is sliding down a ramp with no friction. However, we have to divide by this factor in here, which is 1.5, to get the answer for our acceleration. And so in the end, let's see what we get. 9.8 times the sine of 20 and divided by 1.5. So it's 2.23, or if we're going with direction 2, negative 2.23 meters per second squared. That's our answer for acceleration. All right, so that's part 1. Now part 2 is to figure out how big is the force of friction. And I'm going to show you 2 completely different ways of solving this problem. You decide which one you prefer. So in the first method, I'm going to just split this in half. I'll do one on each side. I'm just going to use acceleration equals net force divided by mass. Even if something's rotating, you can always still use acceleration equals net force divided by mass. For that, I'm just going to draw a standard free body diagram that has mg pointing down, Fn perpendicular to the ramp, and friction parallel to the ramp. We don't need to draw these forces at their point of application when we're simply using A equals net force over m. This is a situation where I would tilt the axes because the acceleration is going to be this way, and we want the acceleration to be parallel with one of the axes. You can do the geometric analysis, but this angle right here is going to be the same as the 20-degree angle. One other word that's really important, whenever you're dealing with rotation and linear motion, you have to take extreme care of positive and negative signs and make sure that they're compatible to one another. And so let me just go back to this original picture here, and let's think about the fact that we know the object is going to roll this way. Now that direction of rotation is, my thumb points in, that's the negative direction. And we know that in a linear sense, it's going to go this way. So to be compatible, we know the rotational direction is the negative direction. So we need to also say that this is the negative direction. So this is the negative side of the axis. This is the positive side of the axis, so that the rotation and the linear motion signs are compatible with one another. All right. So back to our force diagram here. I'm going to have to find the components of the force of gravity. Actually, we're really only interested in the x direction, so maybe I'll just find the x component, and that is opposite the 20-degree angle. So the x component is mg sine, since it's opposite 20. And so now if I put that into our equation, A, which we calculated previously, negative 2.23, equals net force. And so we have positive friction, positive because of what I explained earlier, minus mg, and here the mass is not going to cancel out, and I had said that the mass of the disk is 0.25 times 9.8 times the sine of 20, and then that's going to be divided by, again, m. M doesn't cancel out here. So that's the equation that you would solve to figure out what the force of friction is equal to. Let me do that on my calculator and see what we get as an answer. I kind of lost my train of thought there, to be honest with you. I think that is the right answer. But you know what? I'm going to check it by doing it a different way, and we'll see whether I made a mistake or not. But I believe the math there is correct. You can check that for yourself. So yeah, let me show you the alternate way of solving this. I actually think it's easier than the force diagram. The alternate way is to go back and use alpha equals net torque divided by I, but have a different location for your axis of rotation. I'm going to redraw that picture that I had with mg acting at the center of mass, friction acting tangentially, and the normal force acting in that direction. So now what I'm going to do is I'm going to make an axis of rotation at this location. That was maybe the one that you expected me to do originally. And let's see how that changes things. So once again, alpha in this equation can be replaced with A divided by R. Now, what about adding the torques? So now mg doesn't exert any torque because it's acting right at this particular axis of rotation. So the radius of mg is 0. Normal force doesn't exert any torque because it's parallel to the radius. And so the angle between the normal force and the radius is 180 degrees. And the sine of 180 degrees is 0, so we don't have to worry about that. So here, it's only friction that's exerting torque. And the radius, where friction is compared to the axis of rotation, is just the radius of the disk itself, r. The force is our unknown force of friction. And here, the angle between the force of friction and the radius is 90 degrees. Friction is acting tangentially. And again, to be compatible with direction, the torque that friction is creating would have a tendency to make this thing rotate clockwise, and that is traditionally the negative torque direction. Of course, I have to divide by rotational inertia, but here we are rotating, having our axis of rotation at the center of mass. So I simply have to use 1/2 mr squared, which is the formula for the rotational inertia of a solid disk around its center of mass. So that's a really important difference with how we did it last time, that here we're rotating around the center of mass, so I don't have to use the parallel axis theorem. So let's see. Once again, the radius of the disk cancels out. This r maybe cancels out that square, and then this r cancels out the remaining r. When you're calculating friction, mass doesn't cancel out, so that's the only cancellation I can make. Now, A from the previous problem is equal to negative 2.23. So that is equal to negative friction, and the sine of 90 is 1, and then divided by half the mass, which is 0.25. Let's see if we end up getting the same answer that I got last time. Okay, so let's calculate that result there. So 2.23 times a half and times 0.25. And okay, look at that. Our answer for friction is 0.279 newtons approximately. And that is what we got last time. So obviously I did do it right previously.